Hi everyone, welcome back to another session of electronic device. In this session, we are going to discuss about the equivalent circuit of JFET and its frequency limitations. Okay, like our BJT, the JFET also can be used as an amplifier. Okay. If we have a mathematical model of JFET in our hand, it's very easy to analyze the working of amplification using this device. So, in order to analyze the transistor circuits, need a mathematical model or equivalent circuit of the transistor. One of the most useful model is small signal equivalent circuit. The small signal equivalent circuit means we are going to draw a circuit which is valid for a low frequency inputs. Okay, that model is going to change if we apply a higher frequency. So, we are going to see in both cases one by one in this session. And look at this diagram, you can see a JFET with the three lead, source, gate and drain. Okay. And this is N channel JFET, you can see P plus region over here, and we are going to apply a negative input to the gate source. Okay. We have seen the working of this JFET in previous cases. So, the mathematical modeling of JFET, what does it mean? Basically, the JFET, though it is made up of semiconductor, we can represent this JFET using some of the passive elements like resistance, capacitance, okay, current source, all those things. So, we are going to represent this device using the passive elements. We know when we apply a voltage to the gate, this PN junction, which PN junction, this is a N channel JFET, this is a N material, this is P material. So, you can see a PN junction over there. That PN junction is going to be a reverse bias condition. So, reverse bias condition that we know. Okay. So, here depletion region is created, and as soon we increase the gate voltage, depletion region will grow into the channel, finally it leads to pinch off. Okay. The depletion region is completely depleted charge carriers, and it introduce some capacitance because either side of this depletion region having charges, positive charges and negative charges. If positive charge and negative which are separated apart using any medium, so it offers some capacitance. That is what the basic concept of capacitor, right? We will be having two parallel plates, right? And one side we apply positive and other side we apply negative. The parallel plate, in between parallel plate either may be air core or dielectric medium, whatever it is, right? It gives a capacitance effect, right? Similar way, there is no charge carriers in the depletion region. So, either side of the depletion region we have a potential, we have a charges. So, it offers some capacitance. Okay, junction this is junction basically. So, junction capacitance between gate and source, that we represented as CGS. Similar way, you can see the capacitance between gate and drain also, that we represent CGD. Okay. And we know when there is a reverse bias across a PN junction, there will be a diffusion of charge carriers which leads some current through that junction, and this diffusion never takes place infinite time. It is for only small time duration, and because the small resistance which we call it as diffusion resistance. So, the diffusion resistance between gate and source I can represent RGS. In similar way, there is a diffusion resistance between gate and drain, that is represented as RGD. That is actually between gate and source and gate and drain. If you consider drain and source, we can see there will be channel, the channel offering some channel resistance Okay, because of the channel resistance we are getting an inclined current characteristics. We know that usually represent R, D, yes, and there will be parasitic capacitance between source and drain, that usually represent not a diffusion capacitance, a parasitic capacitance, that is C, D, S. And in between the drain and substrate, there will be capacitance that we represent using Cs, and you can see the semiconductor offering some series resistance between gate and source and gate and drain, that usually represent using Rs, source resistance, and the drain resistance. So these are the parameters we are going to use to draw the equivalent model of JFET. So we start from gate, so gate will be here, and our drain, I can mention drain here, and our source I can write somewhere here, source, and there will be a RD here, right, RD, series resistance, this is again another series resistance, RS, this is my source. Okay. Between the gate and the drain, between the gate and drain, there will be a resistance. What resistance will be there? Diffusion resistance will be there. That resistance is known as R, G, D. There will be capacitance. These two parameters are parallelly occurring in the semiconductor. So this is known as C, G, D. Okay. Capacitance and resistance are parallelly occurring in the semiconductor, no doubt in that. So it's supposed to draw in parallel. Okay. And between gate and source, we have again a diffusion resistance and junction capacitance. So I'll draw like this, a resistance. That resistance is resistance between gate and source, RGS. Okay. There will be junction capacitance, that is known as CGS. Okay, this is my source here. And between drain and source, between drain and source, what and all will be there? There will be one parasitic capacitor and the channel resistance. Channel resistance is usually represented by RDS, and okay. One second, I need to extend this space. This space is not enough to draw the things, right? And I need to erase this as well. I need a more space to draw this. Yes. So what I have here, I will take little more space. This is my RD drain, and here what I can see the capacitance, parasitic capacitance, right? Parasitic capacitance that represents C, DS, and I can see the channel resistance that represent R, T, S. And we know when I apply the source to the gate, definitely the current flow, definitely this N channel JFET, definitely electron flow from source to drain, right? Then current will be there from drain to source. So that again I cannot neglect while drawing the mathematical model. I need to represent that current also. The current depends on the input voltage VGS. So it is a dependent current source. Current will flow this direction because drain to source, and this depends on VGS. The current ID, the drain current ID is proportional to VGS. Okay, and what is the proportionality constant? ID is equal to GM VGS. So Gm is a proportionality constant. Okay. So this will be Gm VGS. Gm VGS. That is the current, dependent current source. And finally, as I told, there will be a capacitance between drain and the substrate, that is C. So this is what our mathematical model of JFET. So we have mentioned all the junction capacitance and diffusion resistance and series resistance like Rs and Rd, and the current, dependent current, and parasitic capacitance between source and drain, and the channel resistance between source and everything we included in this diagram. So we have represent the semiconductor JFET in terms of passive elements like capacitor, resistance, and one current source. So using this we can analyze the amplification the amplification of JFET can be analyzed using this mathematical model. Okay, so that clear cut diagram you have it over here. So I am erasing all the things, the same thing I have drawn here. So, and you can see the input is VGS, input between gate and source, VGS. It is not a normal VGS, you can see it is a VG dash and S dash. What is the difference between VG dash and S dash? We will tell you now. So VGS is the voltage applying between source and gate is this VGS. This is my VGS, no doubt in that, isn't it? So what is an G dash and D dash? What is my how can I represent my VGS in terms of VGS? And let's see, VGS is equal to, okay, so this voltage, what voltage? VG dash and S dash plus the voltage drop across the RS. This is my source, this is my gate. Whatever the voltage I applied across the gate and source will be VGS. Then this is only VG dash and S dash. So what is VGS is equal to VG dash and S dash plus GM VG dash S dash into RS. How do I take this? The voltage drop across this resistance plus the voltage drop across this resistance will be my total VGS. What is the drop across this resistance? Already given, VG dash S dash. And what would be the voltage drop across this resistance RS? That would be the current into this resistance. What will be the current? There is a current flowing through this path, drain to source, that is nothing but GM VG dash and S dash. So when I multiply the voltage with the resistance, I will get a voltage with the current with the resistance, I will get a voltage. So add these two voltage, that will be the VGS. So finally what can I write? VGS is equal to 1 plus GM into VG dash S dash. So this is the difference between this VGS, VG dash S dash and VGS. Okay. I hope you understand about the difference between exact VGS and VG dash and S dash. Okay. Shall we proceed? The same thing I have written over here. I will just read out and go. The VG dash S dash is the internal gate to source voltage that controls the drain current. The RGS and CGS parameters are the gate to source diffusion resistance and junction capacitance. The parameters RGD and CGD are the gate to drain resistance and capacitance. The resistance RDS is the finite drain resistance. Okay. The CDS capacitance is mainly to drain to source parasitic capacitance, and CS is the drain to substrate capacitance. Okay. This is all we have taken in account that we assumed taken into the account by assuming a low frequency model. Okay. So, in ideal case, okay, low frequency a small signal analysis. At low frequency, what will happen to this circuit? At high frequency, what will happen to this circuit? We are going to see now. At low frequency, what is the case? Before that, I would like to introduce a term called capacitance reactance. What is the meaning of capacitance reactance? It is very simple concept. It is the resistance offered by the capacitor. So, like we have a resistor in our hand, right? It offers some resistance. That means it offers some resistance against the electron flow, which in turn give the resistance to current, isn't it? Similar way, the capacitor, so far we learned the capacitor will charge and discharge, but in same time it offers some resistance to the current flow as well. So, that resistance is represented as reactance. Okay. So, what is the reactance? Reactance we usually represent using term XC. So, that is equal to 1 by 2 pi Fc. That is inversely proportional to the frequency. So, now we are going to treat this circuit at low frequency. What will happen at low frequency? This term is low, the frequency term is low, capacitance is constant, 2 is constant and pi is constant. When the frequency is going down, what will happen to the reactance? It is going to increase, right. So, at low frequency, the capacitor offer a high reactance, that means high resistance to the current flow. This is this equation. So, at low frequency, I can say it is open circuit. That means there is no current flow through the capacitor. Okay, because it offers high resistance, it's equally into infinity, almost infinite. So, I can consider it as a open circuit. And what about this diffusion resistance and everything will be a open circuit in the low frequency concept. And if that is the case, how do we draw our equivalent model of JFET in low frequency? I need to omit all the junction capacitance and I need to remove all the diffusion resistance. I need to remove this, I need to remove this, I need to remove this, okay, I need to remove this, I need to remove this, all the resistance, I need to remove everything, and only thing remaining is a current, dependent current source. Let us see that diagram at, yeah, this is the diagram. You can see at small signal, when we apply a low frequency signal, this is the equivalent diagram of our JFET. From here, what I can write, my IDS, the current between drain and source is equal to just a gm VGS. Okay. So, the effect of the source resistance can be determined as follows, and the effect of source resistance is very important, okay, irrespective of other, rather than other, considering other resistance, we have to consider this the source resistance which is in series. Okay. Let us see if this is the case. Okay. IDS is GM VGS. Okay. The relationship between VGS and VG dash and S dash can be found from this expression. It's already explained before. Okay. From this expression, I can write what is VGS. I can write what is VG dash S dash, and I can substitute the same thing here. Okay. If I do that, my IDS is simply GM divided by 1 plus GM RS into VGS. Okay. What we know IDS is equal to GM VGS. That is from this diagram we concluded that, okay, if there is a source resistance, what will happen to this drain to source current? That is what we are going to see. So, we know that IDS is equal to GM VGS, and the VGS can be found from Vg dash and S dash, already explained just now. So I will be getting 1 plus Gm Rs into Vg dash and S dash. Okay. So I am going to substitute for this term from this expression. What is Vg dash and S dash? That is nothing but Vgs divided by 1 plus Gm Rs. So I am going to substitute this term here and I will get this. Ids is equal to Vgs Gm. Vgs into Gm, right? This Vgs into Gm, okay, 1 plus Gm Rs. This term I am going to represent G dash M. G dash M. So finally the IDS is equal to Gm dash Vgs. The effect of source resistance is to reduce the effective transconductance or transistor gain. So this is the technical term being used for representing Gm. Gm is nothing but the gain or transconductance. So look at this. This Rs value is available in the denominator. Since it is available in the denominator, if Rs value is increasing, what will happen to the total gain of the transistor? It's going to, the total term is going to, that means the Gm dash, the total term is going to reduce. Okay. Let's see this graph. It gives the relationship between Gm and Vgs. In y axis have taken Gm or G dash, and x axis we take and Vgs. So what will happen, how this is going to vary? Okay. Look at this. When as on increasing the Vgs in the negative voltage, at minus 1 voltage you can see the Gm value and G dash M value. So which is more here. Okay. As on increasing this Vgs voltage, you can see Gm is almost equal to G dash M. Okay. So in general expressions, what we consider, Id is equal to Gm Vgs. We never mention G dash Ms because we apply almost 3 to 4 voltage in practical application. At that particular point, as this graph shows, the graph itself explaining at a high voltages, the Gm and the Gm dash is almost equal. So that in general expression, we take Id is equal to, that means the drain current is equal to Gm Vgs. Okay. So I think it's clear with the small signal model and the parameters and about the drain current expression. Next we are looking for the frequency limitation factor of JFET, and one more thing, cutoff frequency. So what is the meaning of the cutoff frequency? What is a physical interpretation of cutoff frequency? Okay. So I am going to apply some sinusoidal voltage to JFET. It is amplifier. Okay. One amplifier, I developed one amplifier. I am going to apply a 1 kilohertz frequency signal to amplify. It works, no problem. If I apply 10 hertz frequency to that JFET, it may not work properly. You cannot find out the amplification at the output side. And I increased. Now the frequency is 1 kilohertz. Okay, yeah, it's working fine. I'm getting a proper amplification. I increased the frequency to 2 kilohertz. Still it is working fine. And the output is again, it's improved. I'm getting more amplification. And I am again increased that input frequency to 3 kilohertz. Okay, 1 kilohertz. Now it is 2 kilohertz and 3 kilohertz. And my input voltage is at 1 kilohertz. Just assume I applied just a 100 millivolt to amplify. I got almost 0.9 voltage. Okay, I increased that frequency of input to 2 kilohertz. Okay, I can see the improvement in the output voltage. It become 1.5 volt. Okay. Again, I increase the input frequency 3 kilohertz. Okay. Again, I can see the improvement in the output of 2 volt. So I'm very happy. I'm planning to keep on increasing the frequency like 4 kilohertz, 5 kilohertz, 6 kilohertz. Like I'm going to increase the frequency as if I'm thinking that I'll get a better output voltage at the end. But unfortunately, it's never going to happen. Okay. So just assume the cutoff frequency is equal to 4.5 kilohertz. 4.5 kilohertz. Okay, till 4.5 kilohertz you are getting a better performance 2.5 volt. But when you increase the voltage above the cutoff frequency, your output amplitude is going to reduce again to 2. Again, if you increase that input frequency, it's going to be 1.5. And if you increase 10 kilohertz, you will get almost 1 volt output. So cutoff frequency is the frequency where you can get a maximum performance in that amplifier. That is the meaning of physical meaning of cutoff frequency. So you cannot increase the input frequency beyond the cutoff frequency. It never gives a better performance after cutoff frequency. That is what the meaning of cutoff frequency. So there should be some parameters which limits the cutoff frequency. There will be some parameters which limit the frequency of operation. So if take this example, the frequency of operation, I can say the best frequency of operation, this amplifier 3 kilohertz to 4.4 kilohertz or 4.5 kilohertz. Okay, best working frequency. So there in that frequency range you will be getting a better performance as per my design. That is the concept, that is the meaning of frequency limitation and cutoff frequency. If you work in 1 kilohertz, it may not be give a correct or desired output. If I work in high frequency like 6 kilohertz and 10 kilohertz, again it won't give a proper or enough or desired output voltage. So it's a limited, frequency is limited 3 kilohertz to 4.5 kilohertz, right. Some parameters are there to limit this frequency of operation. That's what we are going to explain now. The first thing is a transit. There are two frequency limiting factor in JFET. The first one is channel transit time. Channel transit time. That means the time taken of a charge carriers to move from drain to source. Transit time. Just assume the channel length is 1 micrometer, right? And the velocity of electron, saturation, maximum velocity of electron, the channel is 1 into 10 to the power 7. Okay. So the transit time I will get some 10 picoseconds. So if it is more, that means the transit time is more, within a short span of time I will be getting a better current, so it actually improves the frequency of operation. Okay, if it is less, it's again going to limit the frequency operations. That's all about the transit time. But at the high frequencies, the transit time is not a matter. That's what the other conclusion you can read it from the materials. The channel transit time is normally not limiting factor except very high frequency device. Okay. So that's what you will be getting the information from some readings. And apart from that, one important thing is the capacitance which is available inside the JFET. Okay. So I'll draw the capacitance which is available here. We have, this is my source and this is our I draw the capacitance figure of JFET. Gate, this is gate, and drain. In between we have a capacitor called this is a gate and this is drain CGD, and here we have a capacitor that is CGS. Again, here also we have one more capacitor, it is CDS. This is my source, gate, source and drain. Okay. So this is a diagram, only capacitor I considered. I suppose to add the figure to this slide. Very sorry, I didn't do that. So I draw this diagram. So here we are going to apply the voltage, right? V G dash S dash, or in all together in between the gate and source I am applying VGS. As the frequency of the input signal VGS is increased, okay, we know that capacitance, resistance or reactance is equal to 1 by 2 pi Fc. So the frequency is increasing, what will happen? The frequency denominator is increasing, what will happen to the reactance of capacitor? It's going to reduce. Okay. So as on increasing the frequency, the impedance of or the reactance of CGD and CGS is going to decrease. So these two impedance or the resistance offered by these two capacitor is going to reduce. It almost like a short circuit, and whatever the current flow through this. So I suppose to draw one more thing here, I forgot to draw that. It's a current, there is a current that is a V G dash S dash into GM, that's also required. Okay, the current is flowing, right? The current flowing in this direction, that is IDS. IDS is flowing this direction, and as on increase in the frequency, there is an input current also flowing that. So I am representing II and IDS. And as on increase in the frequency of VGS, what will happen? The impedance of these two capacitors are going to reduce. What will happen? The entire current is going to flow through this capacitor, because the impedance offered by the capacitor is very less. Then what will happen? If it is entirely zero impedance, it acts as a short circuit, and what will happen? The output current ID is going to be very small value when we increase the frequency, because II and IDS are opposite in nature, right? Opposite nature. So resultant current only available at the output side. The between drain and source, the resultant current will be available. That means if I take a modulus value, it may be IDS minus II. That will be the output current ID. You can read if there is a high frequency operation. Okay. So then if the capacitor is taking a small time duration in order to charge, capacitor will always charge, we know that. Okay. Capacitor, once it charge, what will happen? I told you, as I told you, it act as a short circuit. So if the capacitance charging time is the limiting factor, if we consider that is a limiting factor, then the cutoff frequency can be defined as the frequency at which the magnitude of input current II is equal to the magnitude of ideal output current GM VGS of the transistor. So once it completely charged, right? Okay, if that is the limiting factor, if we consider, then the cutoff frequency is defined as what? The frequency at which the magnitude of the input current is equal to the magnitude of output current. Okay, that is why when we increase the frequency, we will be getting a less output current, which leads to a less output voltage. So these are the two parameters. One is transit time, and other is the capacitor charging time. Which capacitance? The internal capacitance available in the JFET. What are the internal capacitance? That is the junction capacitance available between gate and drain and gate and source. So, these are the two frequency limiting factors. Okay. And see, then how do we write expression for that frequency? Okay. Let us see that. You can see this equation. The equation seems to be tough, but I will solve it for you. The current is equal to what? Current is equal to V by R, voltage divided by resistance, that is the current. And in this situation, what is our current? Our input current. Okay. What is input current? And what is the voltage? This is the VGS. What is the resistance? Is offered by the capacitor, that is actually my impedance. What is the impedance equation? XC. XC, that is a 1 by 2 pi f C, right. What is C here? What is C here? You can see the C is basically CGD and CGS. And if you look into the circuit, I can say this is a parallel in nature. CGD and CGS are parallel in nature. If two capacitors are in parallel, the equivalent capacitor will be the sum of those two, we know that. So, this is actually impedance. Z is equal to XC is equal to 1 by 2 pi f into C GS plus C GD, isn't it? So, I am going to substitute the Z value here, and what is my I? I is equal to my ID. This is what we are going to just explain for cutoff frequency when these two currents are become equal. Okay. Then VGS divided by 1 by 2 pi f CGS plus CGD. So, denominator will go up. So, VGS into 2 pi f CGS plus CGS plus CGD. Okay. That is what you can see here, and one alteration what they did in this CGS plus CGD, that I can see capital letter G. So, I can write VGS 2 pi f into CG here. This equations are same, that is equal to my ID or II, that is given in the equation, that is actually GM VGS. Now, I can find equation for F. What is equation for F? Just a mathematical arrangement you do, you will get that. Okay. Nothing but this VGS and VGS will cancel each other, right. So, GM by 2 pi CG. This is equation for cutoff frequency in JFET. And there is a one equation for GM, there is another equation for CG is available in the textbook, and it's already derived in previous section of the same chapter. It's not mentioned in the syllabus. So, I am not taking that complicated equation for GM and CGS. You feel it's a complicated equation. So, I'm stopping the cutoff frequency equation at this point. So, that is how you got this expression, and from there you will get this expression. Finally, the cutoff frequency can be represented as GM into 2 pi CG, where CG it's supposed to be capital letter, okay. CG, that CG is equal to CGS plus CGD. Okay. So, this is the frequency limiting factor of everything. Okay. Thank you guys.